Okay, there we go. We're recording now. So I'm going to share screen. Good morning, everyone.
Morning.
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 Okay, you should be able to see this about now. Everyone see section 2?
Yep.
Okay, so I changed this from, in order to stop from causing more confusion, instead of calling this module, I changed it to section. Okay, so it was lecture first, then it was module, now it's the section. Maybe Professor Eager, you can tell me if you're not using that term already. Okay. Okay, so this is where we stopped last time. We talked about structural efficiency, and we said that the efficiency of a structure can only really be optimized when you are concerned with both the geometry and the materials. If you just focus on geometry, you won't get an optimal solution, and if you just focus on materials, you definitely won't get an optimal solution. So these two factors are required in order to get the most efficient structures. So before I go any further, I'll just say that remember, you guys can stop me at any time and ask questions. I've baked in a lot of time into the semester overall to allow for questions so we can discuss things. That's really important. I think active learning is very important, so feel free to ask questions, okay? Next slide. Okay, so here's where we're gonna start the next part of this. So we're gonna focus now on the materials side of that equation, okay? And I'm gonna start by presenting these two cars. On the left, we have a Lotus Elise. This is about a 1996 or 97 Lotus Elise. On the right, we have a Renault Spider Sport. Okay, both these cars were introduced in Europe, I think in 96. Interestingly, they're both about the same size. They have very close to the same wheelbase, very close to the same track, very close to the same engine. They're both inline 4-cylinder engines. One's a little bit bigger than the other, but not by much. And having been inspired by the Acura NSX body structure, they were both inspired to make their body structures from putting together aluminum extrusions. Okay, these cars both have bodywork that's very, very thin, made from fiberglass. Okay, so these cars look pretty darn identical. They're both about the same size. They got the same engine, same type of construction, but there is about about 450 pounds difference between the two in weight. Now that's a lot of weight when you consider what a small car is. That's like 28%. So what's the difference? Why is there a huge difference in weight like this? And I'll tell you why. It comes down to the way that the structural members are joined. When you take a precipitation strengthened aluminum and you weld it to another piece of precipitation strengthened aluminum, you get a substantial decrease in strength because you get coarsening or you lose your heat treat in areas that got hot from the weld. We call that the heat affected zone. And in order to compensate for this weakness, it's necessary for the design engineer to increase the wall thickness of the structural member to compensate for the lower strength that's created from the heat affected zone, or from the heat exposure. So the Renault is welded together. They took these aluminum extrusions and they probably, maybe TIG welded or MIG welded them together, and they created these big heat affected zones. They found out that rather than the material having a strength that's up here, it actually had a strength that was down here. And so they had because they can't selectively thicken the area where the joints are where the tubes, the structural members are welded together, they have to make the whole tube thicker, the whole structural member thicker, and they have to deal with the weight of all that. So the brilliant engineers at Lotus recognized this, and they decided to use structural adhesive to bond the car together. Now, this wasn't necessarily such a new idea in the kind of grand scheme of things, because they've been doing this on airplanes for many, many years. But this is really the first time everyone really applied this structural adhesive technology to a car, to a little sports car. It saved them 450 pounds. Bringing this back to the bicycle analogy for any of you guys that are into bikes, this is exactly similar to what they do with bicycles when they talk about butted tubing. So on racing bicycles, steel racing bicycles, for example, they know that if they're going to weld or braze tubes together, there's some strength reduction associated with that heat. So what they do is they just locally at the end of the tube increase the thickness of the tube so that the joint has the strength of the rest of the tube. it's a very effective way at reducing weight. And then the rest of the tube can be very, very thin. In fact, sometimes only a couple hundred microns thick. So they're able to remove weight that way. So here's an interesting point that this strategy that actually been used on bicycles for many decades, prior to the Lotus at least, was applied to cars. Anyway. So how do you make a light structure when you are focused very much on the material side of things? What is it that you have to focus on? So let's just say for the first pass analysis, the items that are most important are the strength, or the yield strength to density ratio, and the stiffness to density ratio. If you can maximize these quantities, the chances are you can build a lighter efficient structure, more efficient structure. Now this is just a first approximation. There's other factors here that are important, obviously. Fracture toughness, energy absorption, fatigue resistance, creep resistance if it's running at high temperatures. But for the purpose of our lectures, we're really just going to focus on these two quantities, just to kind of make things simple and get the idea across of how you design materials for maximum efficiency in a structure. Okay, so this is a key that you're going to see repeated for a while here for the next maybe 3 or 4 lectures about the importance of these two ratios. How strength is this thing per unit of mass, or how stiff is this material per unit of mass? Okay, so before I go on, does anyone have any questions? And you guys? Nope. Okay, we're good? Okay, so designing materials that are strong or designing materials that are stiff requires, unfortunately, a very philosophical background as a starting point to move forward. It looks unrelated, it's confusing, it doesn't look like anything you could very easily apply as an engineer, but we have to start here just so we're all on the same page, kind of set the tone about where we're coming from, what philosophy is necessary to produce materials that have high strength or high stiffness ratios. Okay. A lot of this starts, I think, with Professor Cyril Smith, who was at MIT. In fact, I think I know where his office is in the above the Infinite Corridor. Professor Cyril Smith worked on the Manhattan Project. He was a metallurgist, and he was also very much, I think, into art, and he was into history and antiquities and archaeology and things like this. And he wrote philosophically on a number of topics, but one topic he did write about was on materials. And he talked about materials being really what he called a hierarchy of interlocking systems and subsystems. So that's pretty abstract, I agree. Okay, but what does that mean? What does that look like when it comes to materials? How can I explain that? Now, if you look at this grain right here, this is a grain of steel. Okay, and it's broken up. You can break this up into several different systems on this hierarchy. You can think of the terms of a grain, like they call it a packet boundary. That grain has little blocks in it of different composition. For example, if it was pearlite, it might have some layers of ferrite and cementite stacked up. Okay, so that's a subsystem. If you get a martensitic lath structure, there are almost like little spikes or little needles that kind of fit into each other. That's another system here. So you can kind of see here how you've got this hierarchy of systems. You've got the grain. You've got these things that are inside the grain. Later on, we'll talk about precipitates, which is another subsystem. And this makes a lot of sense. Materials are this sort of hierarchy of subsystems. Okay, so a little philosophical. Hope you guys understand that. I encourage you to ask questions if you don't. Anyone? All right. Another piece of important philosophy for designing materials is the 4 interlock chains which form the fundamental basis for material science. These are the processing, structure, property, performance relationships. So maybe way back in the, I don't know, right after the World War II, or maybe before that, there was a lot of scientists at work, metallurgist scientists at work, who would maybe take a material, heat it up, cool it down, and they would see some structure. They might see that it's martensitic. They might see that it has this phase or that phase, or the grains are this big or that small, or whatever it was. But they then correlated that to a property. Okay, if the grains are small, the material is strong or hard. And then they realized, okay, maybe someday far off, there's some engineer who's going to want a material who's strong or stiff or light or whatever it is, and that's the performance. So scientists for decades and decades and decades went from the left of this interlocking chain to the right. Okay, that's inductive reasoning. That's what scientists do. That's how scientists think. Okay, and it wasn't, I think, until maybe I don't know, the 70s, maybe the late 70s, or maybe early 80s, when another professor at MIT named Morris Cohen, who I think was Professor Eager's advisor. Is that correct, Tom? Anyway, I think Morris Cohen might have been his advisor, but
No, I TA'd for Morris,
okay.
but he was not my advisor. But anyway, the interesting thing about Morris is he had so many graduate students and postdocs, people would hang out in the restroom next to his office in order to be able to see him.
Oh my God.
Okay. Never mind.
That's interesting information. Thank you. But Morris Cohen said, well, wait a second. You don't only go from the left to the right on this, on this chain. There's maybe some ability to go the other direction. That is actually engineer a material, knowing what the scientists came up with, knowing what they learned, knowing the theories that they proposed and proved. Maybe we can actually engineer this material. Maybe we can figure out how to process. We can figure out, okay, we want to build a spaceship. The spaceship's got to be light. We're going to need material that has a high strength to density ratio or high stiffness to density ratio. What structures are there in steel or aluminum or titanium or nickel super-based alloys that are going to give us this strength that we need, the strength to density ratio. So, maybe we need a martensitic phase, or maybe we need austenite, or maybe we need precipitates, or something like that. There's some structure. There's some subsystem of the material that we need that's going to make it strong. Okay, so what properties do we use? How do we engineer those properties? How do we engineer those properties to get that structure, to give us those properties that gives us the performance we want? So in my opinion, it seems that the engineer goes the other direction down this chart. By engineering a material rather than just doing discovery and understanding why it has the properties. Some material has the properties it has. You go the other direction. You go from right to left, which is important. So now expanding, or let's say combining Cohen's reciprocity with Professor Smith's systems approach, you can expand this material. You can expand these different systems and show the subsystems, and understand that there's different processing steps that lead to different structures, and those structures lead to different properties. Okay, so I skipped a bunch of stuff there. In 2011, President Obama, and I guess his staff recognized that, and his agencies recognized that there's a lot to be had from designing materials. That the design of new materials have produced wonderful things for us, like lithium-ion batteries, like steel that doesn't collapse on bridges, like computer screens, all kinds of interesting materials that have improved our lives dramatically, improved everybody's lives dramatically. But the question is the problem was that they've seen that it takes like 20, 30 years in order to go from materials concept or even proving the technology after having a real product that people actually enjoy. And I think, if I remember correctly, like scientists had developed a lithium-ion battery like in the mid 80s. They had actually figured out how to use lithium and make efficient batteries, but I don't think we really saw any really good lithium-ion batteries in the market till like the mid 2000s. So it took like 20 years. And there's all kinds of other examples of this. I mean, there's carbon fiber, composites were around for the Mercury space program, but we never really saw them in bicycles or cars or anything like that for decades and decades later. So in order to address this, President Obama and the agencies created the National Materials Genome Initiative, and they modeled it after the Human Genome Project. So the Human Genome Project was all about understanding how can we fully describe a human being with some data. And the biologists, They understand things like DNA and RNA. I don't understand very well, but they understand these things, and they understand that every human, every animal, every dog, every cat has got this sort of unique DNA, and that can we sequence these? They call it sequence. I don't exactly know what that means, but can we sequence these DNA? Can we come up with these long change of these molecules that would, and a whole sort of huge database of these things that could fully describe a human? And then I think it was maybe in the mid-90s or something, there was another professor, I can't remember where he was at, but he said, well, what about materials? Like, is there something similar we can do for materials? Isn't there like a full database, a full description of information we can put together that would fully describe what a material is? There's
that professor, by the way, was Hertz Sater at MIT, and he coined the term the materials genome. And Barack Obama decided he liked it, so Hertz quit using it and gave it to Barack.
Well,
it's a little intellectual property study for Steve.
Oh, really? It brought lots of money into the field, though, which is great. But
yeah.
So the initiative seeks to put together thermodynamic databases, thermochemical data to describe a material. What phases are available in any material? Some crazy alloy of bismuth or who knows what. What processes get you those? What structures are there? What structures are available? What defect populations are possible in different materials? So to put together this full genome of materials, of all these different things that are possible. And the bigger picture goal of the project is to reduce the time to market by 2x and also reduce cost. It's an interagency effort. So that means that the Department of Defense, the Department of Energy, the Department of Transportation, probably EPA, all these agencies are involved with increasing the body of knowledge of the materials genome. So increasing all the knowledge that's included therein. And it's not just to create like thermochemical databases. It's also to create predictive tools. If you have this microstructure, you will get this strength. Here's this model that you can use to calculate that. So it's interesting. The MGI, the Materials Genome Initiative, it really populates the processing to structure link as well as the structure to property link. So it's focused on the first three links pretty much here. The topic of design of materials. So in this case, like we're talking about designing materials for specific strength and density ratios, I think began with Kaufman and Cohen. You got a question?
Yes.
Sure.
For the previous slides, I'm just curious, like, because we talk about like human genome things, right? I'm thinking about in the field of like material science, do we talk about like an ethical issue? I mean, just a random question. Sorry, just
no, that's right. That's an appropriate thing to ask. I don't have an answer for that. I don't know. It wouldn't surprise me at all if there's some discussion in the agencies about, okay, if we're designing better explosives, is that a good thing or a bad thing? Is that bad for humanity or good for humanity? There's probably those discussions going on somewhere, but it's a completely appropriate question, but I don't have an answer for it. I could get back to you though. Okay, so this concept of materials by design, that's what they called it when I was a grad student. The name has morphed a couple of times, but I think it sort of began in the mid 70s with Cohen and Kaufman, and this paper right here, which I actually have a copy of, it's called the Martensitic transition in nickel and iron nickel systems. I guess this is one of the first. Correct me if I'm wrong, Professor Eager, but I think this was one of the first papers where they started discussing, or scientists started discussing about collecting thermochemical data and then using that to draw phase diagrams. So for any of you guys who maybe didn't have a material science course as an undergrad or whatever, the phase diagram is sort of a map that says at this temperature and this combination of atoms, this composition, you get these different phases. It's a map. But they've been created empirically, but I think this was the first time anyone started talking about using databases, thermochemical databases of materials to calculate phase diagrams using Gibbs free energy equations. So I, as a grad student, I actually wrote one of these programs as part of a course. It was a lot of fun. Maybe you guys will get a chance to do that too. But anyway, the field of materials, Tom, what?
If you want, I can just fill in a little bit on that.
Sure.
Morris Cohen had two postdocs in the early 50s. One was Larry Kaufman, who you've mentioned. The other was Matt Hillert. If you go to the 1970s, and Thermocalc is Matt Hillert's program. Larry Kaufman is the father of CalFad. So you can say they all go back to Morris Cohen, and that was the early 50s. This paper you're talking about probably is one of the first ones that actually did what those guys conceived in the 50s. It took 20 years. The other thing is, so far as calculation of phase diagrams, that was brought here by a guy named Karl Wagner from Germany, W-A-G-N-E-R. And Wagner was a brilliant thermodynamicist, and I could tell you stories about him, but not that I knew him, but my thesis advisor knew him and had everybody in the department had great respect. He stayed at MIT for about 10 years and then went back to Germany. But the real brainchild of this historically going back was Karl Wagner in the 50s.
Okay, thank you. I didn't know that. Yeah, it's a lot of fun. I've done this before. Like I'm sure you guys have all seen, maybe you've all seen phase diagrams. Like I said, it's a map of materials versus, or temperature versus materials. But the boundaries of when one phase forms or different phase forms is all about the thermodynamics and reducing the Gibbs free energy to the minimum possible of all these different things that are mixed together. And it's a lot of fun if you get a chance. I just did it in Excel. It wasn't anything too crazy, but it was pretty cool. Anyway, so Larry Kaufman developed this program, this CalFad concept or CalFad method of designing materials, or not designing, but generating phase diagrams, okay, through thermodynamics, Gibbs free energy, and these incredible databases of thermochemical information. And that eventually sort of, that gives you the possibility to start designing materials, and that you can choose materials based on the composition and the temperature. So that's where the design part comes in. But then this CalFad kind of expanded into the idea of design of materials, which incorporated more into that processing structure link, okay, but also started adding some things having to do with the structure property. So creating predictive models that would allow you to go from microstructure to properties. So given this microstructure, you get this strength. This whole process has really blossomed in a wonderful, elegant, beautiful way, I think, by the government's participation with the Materials Genome Initiative. Okay, and now it became computation materials design, and then I think the current buzzword they're using for this is integrated computational materials engineering, which is understanding or using computer models to create that processing structure link, and then also that structure properties link. Greg Olsen, who's at MIT now, he's had a very large research program at Northwestern University where he developed several steels that ended up in landing gear of airplanes using these methods. And he's really, I think, also one of the big contributors to that field.
Can I ask a question?
Absolutely.
Why do you need computer models to study this? Is it because there are so many factors that go into how a material behaves under certain circumstances, or is it the nature of the materials themselves, the molecular nature of it? Why do you need computer models to study it, and what do they use?
Sure. So let's start with the processing structure link. If you imagine you've got a whole soup full of 9 elements in a steel, for example, you got cobalt, you got chrome, you got moly, you got nickel, you got carbon, etc. And then there's some energy associated with having these things all together, okay, given by what's called the Gibbs free energy. Don't worry about what that is. It's just an energy associated with having these different atoms. But the energy that these things have at all these different temperatures, even a single material, a single element, is a huge database of numbers. Now you start mixing together 9 of those materials, for example, and all of a sudden you've got huge databases, multi-dimensional databases that you or I or any human couldn't quite possibly fathom. So computers are very good at dealing with those sort of things because they don't get tired. Their brains don't fill up with information. They just can iterate back and forth through millions and millions of lines of data and pull out the things they need. It becomes so big, so large, it's not something that a human can really, I think, stuff in their head and understand, more than just sort of a very high level idea. But computers can do that. Now, if you look at the structure property link, there's been, I think, a lot of, they call it ab initio calculations, where they try to go from first principles to predicting the behavior of a material.
Stick with structural materials.
Okay, yeah, it's a little bit simpler, but the point being is that, like, I've seen simulations done trying to understand how phosphorus and sulfur in an iron and carbon steel matrix affect the strength between the different atoms. So there's simulations done where they try to go from, you know, atoms, nuclei, to electron shells and clouds, and how different atoms next to each other interact with one another, so that you can sort of predict how much energy it's going to take to pull these atoms apart with any kind of accuracy. And then factor in there some stochasticity, and it becomes even more complicated. So that's what the computers are needed for.
So it's understanding how these materials behave at a molecular level given certain circumstances, whether it has to do with what they're combined with or how they're being used.
Temperature, right, for example, or, you know, like sulfur is notorious for making materials brittle at low temp, making steel brittle at low temperatures. And I always walk around saying to people, sulfur sunk the Titanic, because the material that they had in the Titanic was so full of sulfur that when it got down below some temperature, you know, maybe 10 degrees Celsius, in the cold water there, close to freezing, close to 0 Celsius, it was brittle. And when it hit the iceberg, it snapped. It didn't deform, it snapped, which left a bunch of gaps open for water to pour in, and the thing sank. So if they had the capability to do the modeling and understand what the sulfur does and predict how tough or brittle the material would be based on how much sulfur there was in there, they might not have sunk. It might have just deformed, and everything would have been fine, and we wouldn't have all these ridiculous movies, right? Okay.
But thank you. I appreciate the explanation. I think I get it now.
You're welcome. I don't think the Titanic was a ridiculous movie. It's kind of interesting. There's been a lot of ships that have sunk in history, and we're so fascinated with that particular one that's sank. Anyway, I am too. I like the movie as well. Okay, so back to this. Again, the fundamental paradigm or framework that we use as material scientists to design materials is the processing, structure, property, performance relationships. And then expanding the levels of those systems, those four systems, you see that there's a series of interlocking subsystems. There's different processes that go into making material. There's different pieces, components, subsystems of the hierarchical microstructure. Those different microstructures not only give you the different properties, but they also interact with one another to determine the properties of the material. So for this lecture, for this semester, we're really going to focus on really pretty much two properties, as I mentioned: the strength to density ratio and the stiffness to density ratio. Those are over here. Because for the most part, at most room temperature or ambient temperature structures, those are the properties that give you the lightest, most efficient structure, that are the biggest levers, the most potent properties that go into predicting or designing lightweight structures. And there's for given material, whether it's aluminum or steel or whatever, there's all these different processes. These processes produce structures. These structures result in properties. So we're going to focus on this is important. We're going to focus on this for the most part for the next couple of lectures: strength to density ratio and stiffness to density ratio. For the next what's left in the lecture here, and for the next little while, we're going to focus on strength to stiffness, or strength to density ratio. We're going to talk about stiffness later, but for right now, we're going to talk about strength. A good place to start with figuring out the best strength to density ratio materials is to start with this thing here called the Ashby diagram. So this particular Ashby diagram is a diagram of strength as a function of density. And this chart is one of a series of many, many charts. Michael Ashby at Cambridge University in the UK he came up with this delightful little tool. And these are a series of bubbles you're seeing here. And these little bubbles encompass the strength to density ratios of a variety of different materials, going all the way from foams to some polymers, to some composite materials, steel, aluminum, ceramics, cement, copper. And this is a good place to start with choosing materials that have the highest strength to density ratio. So you want to pick materials that would be in the furthest upper left, right? So the materials that sort of come into that area are, I think, carbon fiber reinforced plastic. It's hard to beat right here. And yeah, there's a bunch of these diagrams. There's also one of these for stiffness to density. There's ones for toughness to density. There's ones for thermal expansion to density. There's all kinds of these curves. So I said to you before in our last lecture that as material scientists, we're encouraged not to look up book values. We're encouraged to ask what does an engineer need and figure out how we can engineer the material to get us that. And this, I recognize that this table, in a sense, is kind of looking up on the table, this diagram here, this Ashby diagram is kind of like looking up at a table, like what's the best strength material, and let's just use that one. But let's just say that this approach, by looking at the Ashby diagram, it puts us in the right system. It tells us, do we need to be looking at steel? Do we need to be looking at aluminum? Do we need to be looking at copper? It picks that first system, the material system. It helps us choose that first material system. But once we've done that, let's say we pick steel, for example. Then the question becomes, well, okay, so we're not looking at a table. We have to choose a material. We want to design a material. We want to design a material that gives us the best strength to density ratio. How do we do that? The first thing to do after picking the material system is to think about setting goals. How strong the material do you think we can possibly achieve? How tough a material do you think we can possibly achieve through our design? Now, I know this is an example that's about toughness and strength, but let's just use this because it's a nice example, I think. So this is from Professor Olsen. I'm not sure why it doesn't say. I thought I put something in here that called him out. No, it doesn't. Okay, this is from one of Professor Olsen's works. I should mention that. I'll put that citation on here later. But this is a graph that shows fracture toughness versus hardness. For steel, most typically hardness and strength scale with one another. If you have a material that is harder, it's also stronger. And there's actually tables and relationships you can use to go back and forth between hardness and strength. So this graph here shows some currently commercially available materials. These materials fall within these trapezoids, or maybe we can even call them bubbles, sort of like the Ashby diagram. And for example, like, let's see here, 4340 steel is right here. So 4340 steel is a nickel, chrome, molybdenum alloy of steel. It's very strong, very tough. It's sometimes called 300. Sometimes they call this alloy 300. It's used on like, let's see here, driveline components in racing cars where they can afford to use it. It's used in airplanes for like shafts that are heavy torsion or bending loads. It's a very, very strong material. And you can see where that falls in this paradigm of stiffness and strength. Strength, again, is the same as hardness. You can easily get a 4340 to a strength of, I don't know, 55 Rockwell C and still have a fracture toughness of about 50 megapascal root meters. Okay, on the other end of the spectrum, you have this material right here called AF1410. This is a special, I think it's 6 or 7 component alloy steel with cobalt, chrome, nickel, moly. And this is a material that was specifically developed by the Air Force, that's why it says AF in front of it, to be used in landing gear. So landing gear of airplanes is a big challenge because, you know, they take a lot of impact loading, right? Or an airplane lands on an aircraft carrier or runway somewhere, and they're very small and skinny. You've got this multi-ton aircraft that's landing on those tiny little sticks. They take a lot of stress. And of course, because it's an airplane, it's really critical to make them lightweight. So you can do whatever you can to design a material that has the strength, the density ratio to handle that type of loading. So AF1410 was developed and is a very strong material. It's also a very tough material. So they're able to achieve fracture toughnesses up in the over 150 megapascal root meters. and at the same time have Rockwell C values sort of in the, I don't know, mid 40s, or I'm sorry, between 45 and 50 Rockwell C, which translates to, I don't know, a gigapascal in yield strength or so. It's a pretty strong material, but it's not as strong as 4340. So in setting goals, the important thing to ask is what features of the microstructure about the 1410 are different than those of the 4340? What's giving you the strength? Okay, the higher strength in the 4340. What's giving you the toughness in the AF 1410? And is there some way we can engineer a material that would have those two types of microstructures, or features from those two types of microstructures, to give us a material that's both stronger and tougher? And that's what this red box is right here. This red box is, if you take some of the microstructural features of each of those two materials and combine them together, it's reasonable to say you could end up in this box, this red box right here. So that's a way a material scientist sets their goals. They look at the different advantages of each of these materials, and they combine them into one to create a material that has both properties. And this is a good place to start. So the goal of designing a material based on this information would be trying to have a hardness that's sort of between 55 and 60, but still maintain 2 times the fracture toughness between 150 megapascal root meters. That's goal setting. With steels, with aluminums, with metals, we have a number of microstructural features that we can call upon, that we can scrape up, put them together to design a material that meets our goals, like we discussed on the previous page. One of them, this is a list going from small to bigger. At the very atomic level, there are what's called interstitials or substitutional atoms, okay, that go within this lattice of atoms of a material. These atoms that sit at either interstices between atoms, or they actually sit at a lattice location. We have something called a dislocation, which is like a missing column of atoms, and this is a transmission electron micrograph showing a dislocation. So right here, you can see there's these rows of atoms here. You're looking at a column of atoms actually edge on. This is taken using a transmission electron microscope. But right here, you can see there's like a missing atom or something, a missing column of atoms right here. You guys see that? That's what's called a dislocation. A missing column of atoms right there. The next thing, another microstructural feature is like in martensite, where we have these sort of interlocking needles, or they call them laths. Then in aluminums and also in steels, we have things called precipitates, which are a little bit bigger typically. And these are little sort of second phases that form in the material, kind of like very similar to like the way rain forms in clouds. You've got this material, they call it a matrix of material that's could be some particular, I don't know, it could be iron with a little bit of carbon, it could be pure aluminum. But then you've got these little particles that precipitate out of the matrix because it's thermodynamically favorable. If you alloy this material with silicon or magnesium or some other elements, or chrome or cobalt, you can get these little precipitates that come out of the matrix. And these little precipitates can be so small that you can't see them with an optical microscope to big enough that you can see them at relatively low mag on an optical microscope. This is sort of like raisins in a piece of raisin bread. Think of it that way. Then we have some features that are a little. Someone have a question?
Yeah, I was wondering with the laths, I'm having a bit of trouble seeing what exactly we're looking at in that picture.
Okay, well, thanks for the feedback.
You mentioned there are kind of needles that
right.
interlock.
I'll get you a better picture, but this is a steel, and the length scale here. This is a micron. This little needle marker right here. And then there's these little tiny needle structures that kind of interlock, almost like hay. Okay, and what you're looking at here is the little needles. I probably could have come up with a better picture.
Gotcha.
But this is here. You can see Cyril Smith subsystems, right? There's sort of a packet of material here, and then there's these martensitic little needles over here. 2 different subsystems shown in one micrograph. Make sense?
Okay.
I'll get you a better picture.
Thank you.
Okay.
All right. Thanks.
So and then there's bad things that are also subsystems like inclusions. Okay, inclusions, manganese sulfur inclusions help sink the Titanic. Then we start talking about grains, which can be a little bit bigger, and these are how materials form. I once heard a analogy on grains and how they formed from the late Carroll Smith, who was a brilliant race car and well-known race car engineer. And he said that if you have a bunch of atoms, if you think of a bunch of atoms as a bunch of soldiers walking around a field. So if you have a bunch of atoms at high temperature, you've got these soldiers walking around a field. The soldiers are walking on the field because it's a hot day, they're all walking around kind of randomly, just like atoms would be if the material was hot. They're not forming any kind of continuous order. They walk around, they're random. There's all these things jumping around, these little atoms. And then if you drew sort of lines at random orientations on this field, you told the soldiers at a certain time, at time 0, line up behind each other on these white lines. And then all the soldiers filled in the distances between these white lines, and you'd have what are grains. It's the same thing as atoms going from a state of being in flux and moving around in random orientations and motions to forming up in these lines and then filling in the distance between the lines in an ordered array, i.e. a lattice. That's how you get grain. That's a grain structure. But let's not forget that the area between the grains can be interesting too. And there are lots of strategies materials engineers use to engineer the grain boundaries to produce certain properties out of the material. I think at the sort of foundation of strengthening metals is this thing called the dislocation. And I describe those right here. That's up here under dislocations, the missing column of atoms. If you look at the strength between atoms and you calculate, you sort of scale that up into a bulk material. So you go from tiny little angstrom-sized atoms and you scale that up into a bulk material. You can reasonably calculate a strength from doing that. Okay. The problem is that if you do that, the strength you get is orders of magnitude higher than real metals, way higher. So why? It turns out that there's these missing columns of atoms that call a dislocation that in reality control how metals deform. They really are the enablers of deformation. They really are the controller of deformation. Therefore, they really determine how strong a material is. It's moving these dislocations through this lattice of atoms that determines the real world strength of the material. And so on the top here, I've drawn a lattice of atoms, and I've shown a dislocation. I've shown that dislocation moving through this lattice of atoms, and you can see how the material going from left to right here has deformed. You scale this up over billions and billions of atoms, and then you can see how this would translate into a real world bulk deformation that you can see and obviously take advantage of to form things out of steel or aluminum. Now, you can also think of this, or you should think of this in terms of 3Ds, right? So there's a third dimension here. These atoms go into the page, and that's what I've shown below, that you have these planes I've drawn here. These represent planes of atoms, and that you can have a dislocation where several atoms are missing, and all these missing atoms line up to form a column. And then you can start thinking of this column as a line of dislocations. And this line of dislocation moves through the material as you deform it. And that's how metals deform. In reality, it's interesting. Even though a grain of an atom may only be, 10 microns across, 10 microns wide, if it's an equiax grain, within a small amount of material, a couple square millimeters, you can have several hundred kilometers, seriously, of dislocation line. So that gives you an idea like how small this really is we're talking about. A couple hundred kilometers of dislocation line in a little tiny millimeter by millimeter little cube. Think about that. So now we're going to kind of go down through the strengthening mechanisms, and I think we're going to run out of time here in about 5 minutes. But we're going to see how many strengthening mechanisms we can go through here. The first, we've talked about, just to kind of back up here and just review. We've talked about structure. Here are some real structures. These are real subsystems and structures in materials. These are tools. Think of these as tools. As a materials designer, you have these tools at your disposal to use to try to strengthen your metal. Okay. You're trying effectively in the real world, what you're really trying to do, what's really determining the strength of the material is how much you can retard the movement of these dislocations. If you make it easy for these dislocations to move through a material, it's not going to be very strong. If you make it really hard to get these dislocations to move through the material, it's going to be stronger. And you can get to the point maybe where it's so hard to move these dislocations that it's easier just to fracture between atoms. So one mechanism of strengthening that we have at our disposal as materials engineers is work hardening. So if you take a metal, even like a paper clip, and you wind it back and forth over and over again, you cycle it, you'll see that it gets heavier to bend each time. And what's happening is that as you're bending it, not only are you moving these dislocations, but you're also generating new dislocations as you're moving it. These dislocations tangle with one another. They tangle up with one another and impede each other's movement. So that's why when you take a piece of steel or a piece of aluminum or copper and you deform it, it gets stronger because you're intertwining these dislocations so that it takes more and more energy to get these dislocations to move through the lattice. The strength that you can get from work hardening, a rough estimate, is given by this equation here. Okay, and what this basically says is it says that the strength, or as the density of dislocations, in this case I've used psi. Anyway, this thing here, I forgot the Greek letters. Anyway, as that density goes up, the strength of the material goes up. The increment of strength goes up with that density to the 1/2 power. And then on the left here, on the right here, sorry, we have this graph that shows how the properties, in this case strength, go up with cold working, and how as they go up, the elongation to failure goes down, and the reduction area goes down as well. Another very potent method for strengthening materials is called substitutional strengthening, okay, or also called solution strengthening as well. And what this is taking an atom and then placing it in another material. So you have the bigger matrix of material, you call that the solvent, okay, and then you have these extra atoms that you're putting in, you call those the solute. A good example of this is steel. In steel you have iron, which is the solvent, and you have carbon, which is the solute. You stick all these little carbon atoms in there. In some cases, the atoms take up lattice locations. That's called substitutional strengthening. And in some cases, they take up interstitials. They find themselves between the atoms in the little spaces between the atoms. This is called interstitial solution strengthening. The one on the right here, interstitial solution strengthening, is actually much more effective at increasing the strength of materials. And this is what's used in steel. Substitutional is what's used in copper and zinc. That's brass. Okay. Here's an interesting processing structure link. We learned as materials scientists the size of the atoms that are more likely to become interstitial and those that are likely to become substitutional. Okay, and this is based on the size of the atom, right? Which is, I guess, a good proxy for the size of the atom is lattice parameter, which is the sort of this distance here between the atomic planes. So it turns out that atoms that are with solute atoms that are within about 15%, plus or minus 15% of the size of the solvent atom are more likely to take latticeates, that is, form a substitutional alloy. When they get much smaller than that, they're more likely to become interstitial, like shown on the right here. Okay. Another factor that helps you predict whether an atom becomes substitutional or interstitial is the valence. So if you remember from your chemistry days, you've got these electrons floating around the nucleus, and some of them can go off to other places and join other atoms and so forth because they're extra, or another atom has to gain some because, how does this work? Valence. It's the difference between the amount that you need to form what do we call it? The inert metal, the inert gas or atoms. You know, in order to get from, you've got so many shells floating around so many electrons floating around the nucleus, and then the atom always wants to get to the point where it's closer to an inert electron structure. So the ones that are the difference between those are the valence electrons. And it turns out that the number of valence electrons per atom, you can also use that relationship to determine how likely material is to strengthen, how likely it is to be interstitial or substitutional. So that shows here that these materials, when you have a copper alloy and you start putting in things like zinc or gallium or aluminum or germanium, you put in germanium, it actually becomes stronger because it's one of the reasons you can predict that is because you know that its electron to atom ratio is higher. The more solute you put in general, the stronger the material becomes. And that's what this graph in the lower right shows. Okay, that as you put in more of these solute atoms, the material strength goes up and up. Precipitation hardening. I think this is probably going to have to save this for next time. Okay, guys, so we will start at precipitation strengthening next week. Does anyone have any questions? Anyone? Okay, good. It's hello? Okay.
I've got some questions about specifically about INVAR and what you know about that, but I think I'll save that for next time after I see the rest of this lecture.
Okay, great. Okay, so we're good, guys. Again, I always want you to stay focused on the idea of design of materials. I don't want you to worry too much about exactly how these different mechanisms of strengthening work. Just focus on understanding that these are tools that you can use in this materials paradigm of the links, the processing, structure, property, performance. You can use these tools to strengthen the material by using that. You can use these tools to strengthen the material. And next week, like I said, we'll start a precipitation hardening. Okay? Until next week, guys. Thanks.
Thank you.
Thank you.